All right, welcome to Indefinite Integrals and the Net Change Theorem. In the previous lesson, we went over the fundamental theorem of calculus, and that helped establish a connection between antiderivatives and definite integrals. And because of this connection between antiderivatives and integrals, the notation that we used for definite integrals is also used to represent an antiderivative of a function. So this integral sign here, when we studied it previously, it had limits of integration because it represented the area underneath the curve of a function. Now we're going to write it without limits of integration, and that's why it's an indefinite integral. And what it means is when you evaluate it, to compute the antiderivative of lowercase f of x dx. And we've already evaluated or computed antiderivatives before, but it was spelled out for us in the directions, find the antiderivative of this function. Now, when you see the integral sign, it basically means to do the same thing when there aren't limits of integration. So the process is the same as before. If you have the indefinite integral of a constant times a function, you can take the constant out. Integral or antiderivative of k dx is just kx plus c, and so on. You can read through the list. Your trig functions are all there, and general power rule, increase the exponent by 1, divide by the new exponent. As long as it's not 1 over x, then you have natural log of absolute value of x, and so forth. So let's just dive right in and look at some examples. And the most important thing is just don't forget the plus c. All right. Good, so find the general indefinite integral. First things first, I want to rewrite my integrand so that it's an integral-friendly format, meaning I want to rewrite my exponent. So I have x, instead of square root of x cubed, that's x to the 3/2 plus x to the 2/3 dx. And then we can just go through term by term, anti-differentiate, which is the same thing as finding the indefinite integral. And I'm going to increase the exponent by 1, divide by the new exponent. So I'm going to have x to the 5/2. Dividing by 5/2 is the same thing as multiplying by 2/5 plus, and then this is going to be x 2/3 plus 1 is 5/3, so the coefficient's going to be 3/5 plus a c. All right, so that one's done. All right, example 2. I have integral of v times the quantity v squared plus 2 squared. Okay, so first we're going to have to expand v squared plus 2 squared, so that's going to give me v to the 4th plus 4v squared plus 4 dv, and then distribute that v through, so we have v to the 5th plus 4v cubed plus 4v dv. And then I can go through anti-differentiate term by term. Make sure you're writing dv until you anti-differentiate. So antiderivative of v to the 5th, that's going to be 1/6 v to the 6th. Antiderivative of 4v cubed, I'm going to have v to the 4th and then divide by 4, so the 4 cancels, so it's just v to the 4th. I'm going to have v squared and then divide by 2, so now it's 2v squared and then plus c. Okay. Good. Ooh, come back. Nice. Example 3. I have integral of secant times the quantity secant t plus tan t. So let's distribute the secant. So we'll have secant squared t plus secant t tan t. dt. Don't forget that dt, otherwise it's wrong. Okay. Well, I'm pretty much done because I know the antiderivative of secant squared, or at least you should, and I know the antiderivative of secant t times tan t, right? Antiderivative of secant squared is going to be tangent t, plus antiderivative of secant t tan t is secant t plus c. So if you didn't learn your trig derivatives, you're going to have a really rough time with this section because now you have to go backwards. Okay. Integral of sine 2x over sine x dx. So I can rewrite the numerator using my double angle identity, right? So sine 2x is 2 sine x cosine x, and then the denominator is sine x, and I can cancel out those sine x's, so this is looking good. And I have integral 2 cosine x dx. Okay, so what's the integral or the antiderivative of cosine x? Well, it's just going to be sine x, right? And then the 2 comes along for the ride, so you have 2 sine x plus c. Okay, nice warm-up example. Let's move on to some other examples. This time, we have limits of integration. So you will not have plus c at the end of your computation. Your result should be a constant, right? Remember, when you have limits of integration, this integral represents the area underneath the curve. So you're not going to have a function. Okay, so first thing I notice, again, I need to multiply out the integrand. So I have integral from 0 to 4. I'm going to have 6v squared minus 2v plus 15v, so plus 13v minus 5. Don't forget the dv. I haven't integrated yet. As long as you have an integral sign, you need a dv or d whatever the variable is. Okay, now I can antidifferentiate. So antiderivative of 6v squared, that's going to be 2v cubed plus 13 halves v squared minus 5v. The constants just always pick up a variable, and then I'm going to evaluate this from 0 to 4. All right? Good, so let's plug in the upper limit of 4. So this is going to be 2 times 4 cubed plus 13 halves times 4 squared minus 5 times 4. That's the upper limit. Minus, and then if I plug in 0 for the lower limit, everything's 0. So 2 times 4 cubed, that's going to be 2 times 64, so 128 plus, so 4 squared is 16, and then that'll cancel with the 2 in the denominator, so that's 8 times 13 is 104, minus 20 gives me 212. Nice. All right, next example, I have integral from 0 to 9 of square root of 2t dt. Now, I could integrate the square root of t just fine, but it's that 2 that's giving me some problems. So what we're going to do is move them apart. So I'm going to rewrite this as 2 to the 1/2 power and then t to the 1/2 power dt. And a constant, right, just comes along for the ride. You just pull it out of the integral. So this is going to equal 2 to the 1/2, and then I'm just going to antidifferentiate t to the 1/2. So that's going to become t to the 3/2, and then I'm going to multiply by 2/3, right? Dividing by 3/2 is the same as multiplying by 2/3. And then I'm going to evaluate this from 0 to 9. All right, so let's see here. What do we have? I have 2 to the 1/2, that's rad 2, times 2/3 times 9 to the 3/2 minus 2/3 times 0 to the 3/2. Okay, so this is just 0. Now 9 to the 3/2, whatever the denominator is, you take that root of the number. Okay, so since it's a 2, I'm going to take the square root of 9, that's 3, and then you raise it to the numerator. So 3 to the 3rd power, that's 27. And then multiply 27 by 2/3, so I'm going to divide it by 3, it's 9. And then multiply by 2, now it's 18. So this is 18. Okay, so you don't need your calculator for anything. You got this. So this is 18 rad 2. Okay, that was a fun one. All right, next we have integral from 0 to pi over 3 of sine theta plus sine theta times tangent squared theta over secant squared theta d theta. All right, so the integrand needs some serious cleaning up before we can go ahead and antidifferentiate. And there's a couple ways actually you can do this. Some of you might notice an identity staring at us, but if you didn't, I would say start off, just split the denominator under each of the terms in the numerator. So you can write this as 0 to pi thirds sine theta over secant squared theta plus sine theta tangent squared theta over secant squared theta d theta, right? Okay, Now from here, what would you do? I would try writing things in terms of sines and cosines to see if it helped clean things up a little bit. So I can write this as integral 0 to pi over 3. You have to write the limits every single step, okay? Otherwise it's wrong. So I have sine theta. If I have secant squared theta in the denominator, that's the same as multiplying by cosine squared theta plus, and then I'm going to do the same thing in the next term. So I have that sine theta cosine squared theta, because that secant squared, right, can come up to the numerator as cosine squared. And then tan squared, I can rewrite that as sine squared theta over cosine squared theta d theta. All right, now look, these cosine squared thetas cancel out, so that's nice. And I have the integral from 0 to pi over 3 of sine theta cosine squared theta plus, here's the sine theta, here's the sine squared theta, so that leaves me with sine cubed theta d theta. Okay, what now? Well, I can factor out a sine theta from both these terms, right? They have that in common, so this is integral 0 to pi over 3 sine theta times cosine squared theta plus sine squared theta d theta. And ooh, do you notice something? Sine squared theta plus cosine squared theta is just 1. So really, this problem boils down to the integral from 0 to pi over 3 of sine theta d theta. Yep. Okay, so antiderivative of sine theta, it's going to be a negative cosine theta, right? Because when you take the derivative of cosine theta, you get negative sine theta. Evaluated from 0 to pi over 3. So cosine of pi over 3 is 1/2, so I'm going to have negative 1/2 minus, and then cosine of 0 is 1, so negative 1, which is going to give me negative 1/2 plus 1, so positive 1/2. All right. Did someone notice an even faster way to do this? Well, depending on how sharp you are with your trig identities, from the very beginning, we could have just factored out the sine theta in the numerator, and then you would have 1 plus tangent squared theta over secant squared theta d theta. And yes, guess what tangent squared theta is? That's secant squared theta. So then it would have just canceled out right there, and then you would have just been left with the sine theta. Okay? So the beautiful thing about math is if you don't notice the quickest way, you can still get there. But if you're sharp on your trig, it'll save you quite a bit of work, right? If you remember those identities. Okay, next example, we have the integral from 0 to 2 of the absolute value of 2x minus 1. Okay, now, the majority of the time, when you run into absolute value functions as a calculus student, you need to rewrite it piecewise. And if you're a little rusty on that, I have a video on the calculus playlist just on how to rewrite absolute value functions piecewise, so check it out. Our function f of x is the absolute value of 2x minus 1. And I'm going to split the domain of my piecewise function where the quantity inside the absolute value is equal to 0. So that's at 1/2. And it doesn't matter which one I make inclusive at this point. So I'll just have one t is greater than or equal to 1/2, and the other one t is less than 1/2. I could have done it the other way. It could be t is greater than 1/2 or t is less than or equal to 1/2. Just don't put the equal on both, okay? So if t is greater than or equal to 1/2, then, oh, it should be x's, excuse me. X. So if x is greater than or equal to 1/2, then the quantity inside here is going to be positive, right? You can plug in a number like 1, 5, anything greater than or equal to 1/2, and it's going to be positive, so I don't need the absolute value. It's doing nothing. And then if x is less than 1/2, then the quantity inside is negative. So in order to make it positive, it multiplies 2x minus 1 by a negative. Now you have to look here at your integral. So from 0 to 2, notice the way my function is being defined changes at 1/2, which is on my interval. So I'm going to need to split up this integral. I'm going to split it up into the integral from 0 to 1/2. Now, how is f of x defined from 0 to 1/2? It's defined as negative 2x minus 1 dx plus, and then I'm going to pick up right where I left off at 1/2, and then I'm going to end at that upper limit of 2. And how is my function defined from 1/2 to 2? Well, that's the interval where x is greater than or equal to 1/2, so it's just 2x minus 1 dx. All right, and then now we can go through and anti-differentiate term by term. So I'm going to have negative antiderivative of 2x is just going to be x squared minus x from 0 to 1/2 plus, and then the other one's going to be super similar, just no negative in the front. So I have x squared minus x from 1/2 to 2. All right. And then now we're just going to substitute in our limits of integration. So I have negative, this is going to give me 1/4 minus 1/2 minus 0 plus, and then here I'm going to have 2 squared, so 4 minus 2 minus 1/2 squared, so that's 1/4 minus 1/2. Okay, and then I'm going to end up with, well, let's see here. These are the same, aren't they? So that's going to give me a positive 1/4 and another positive 1/4, which is 1/2. And then 4 minus 2 is 2. So 2 plus 1/2 is 5/2. All right, beautiful. Next new idea is the net change theorem. So if you have the definite integral from a to b of f of x dx, and that's equal to the definite integral from a to b of capital F prime of x dx, then that's equal to capital F of b minus capital F of a. So what is that saying? Well, remember, capital F is your antiderivative, right, of your lowercase f of x, that function. So the integral of a rate of change, remember, our derivative represents the rate of change, that's equal to the net change. Okay, so we're going to look at some applications now to get a better feel for what this net change theorem is telling us. The current in a wire, example 1, is defined as the derivative of the charge. So I of t is equal to q prime of t. So the charge is q of t. Okay, so q of t is the charge. So the derivative of the charge is the current of the wire. So what does the integral from a to b of I of t dt represent? So let's write out what that would be. So the integral from a to b of I of t dt, that's the integral from a to b. Remember, I of t is q prime of t, right? Well, by the net change theorem, you can think of it like this integral and the derivative undo each other, right? Since they're inverse operations. So if you take a derivative and then you integrate, you just get back the original function, but you're going to evaluate it at the limits of integration. So you have capital Q of B minus capital Q of A. And then let's think. So since Q of T represents the charge, right? And A to B is the interval for T, time, then that means this represents the net change of the charge, Q of T, over the interval from A to B. Okay, so it gives you the net amount of change. Okay, what other situations can we apply this to? Example 2. A honeybee population starts with 100 bees, and it increases at a rate of n prime t bees per week. What does 100 plus the integral from 0 to 15 of n prime of t dt represent? Okay, so this is going to give us the initial number of bees. And then by our net change theorem, this gives me the net change in the number of bees And then look at the limits of integration after 15 weeks, right? From 0 to 15. So 100 plus this definite integral would give me the initial amount of b's plus the net change in the number of b's from that 100. So this quantity represents the total number of b's after 15 weeks. All right. One more scenario to apply it to. So example 3, if f of x is the slope of a trail at a distance x miles from the start of the trail, what is the integral from 3 to 5 of f of x dx represent? Okay, well, f of x gives us the slope of a trail. So say you have a trail and f of x gives us the slope, right? Then that means the antiderivative of f of x would give us the elevation. So it would tell you basically how high up you are. So what does the integral from 3 to 5 of f of x dx represent then? That would be your overall change in elevation from 3 to 5 miles. Okay, good. So you could see this has a lot of applications in physics and other fields. Now let's go back to particle motion. So we've discussed displacement before, but not in terms of an integral. So if we want to compute the displacement of an object moving along the straight line and we have the velocity function, we can do so by integrating along the interval. So if it's from the time interval t1 to t2, and you can compute it by taking the antiderivative from t1 to t2 of v of t dt. And we know the antiderivative of v of t is the position function. So by the net change theorem, we would be left with s of t2 minus s of t1. Now remember, there's a difference between displacement and distance traveled. Displacement is just change in position from the initial time t1 to the initial time t2. Total distance traveled accounts for scenarios where the particle may change direction. So it'll travel more distance than what its displacement seems like. For example, if you've ever had to run the mile, right, in school, and you run around the track 4 times, your displacement would be 0, because where you are from when you started running the mile on the track to where you are when you finish running the mile has not changed at all. But the total distance traveled, that's not 0, right? So that's the difference between displacement and distance traveled. And the issue is this particle, don't worry, he's only running in one dimension back and forth. So it's a less complicated situation. But when you want the distance traveled by an object, in order to make sure the distance covered in the positive direction doesn't cancel out distance covered in the negative direction the way it does when you compute displacement, we have to take the absolute value when we integrate the velocity function. All right, so just be very careful about those two. Displacement, you can integrate velocity along the interval, no big deal. When you need total distance traveled, you need the absolute value of the velocity function, okay? So here we're gonna look at our final example. I have the following velocity function, t squared minus 2t minus 8 from the time interval from 1 to 6. So the problem's asking me to first find the displacement and then find the distance traveled by a particle with the given velocity function. Okay, so let's get going. Part A, we want the displacement. So that's just going to be the integral from 1 to 6 of v of t dt. So we'll have the integral from 1 to 6 of t squared minus 2t minus 8 dt. And I can easily just antidifferentiate term by term. So antiderivative of t squared, that's 1/3 t cubed. Then I'm going to have minus t squared minus 8t evaluated from 1 to 6. Then now I'm going to substitute my upper limit of integration. So I'm going to have 1/3 times 6 cubed is 216 minus 6 squared, that's going to give me 36 minus 6 times 8, that's 48. So that's my upper limit. minus, if I substitute in 1, I'm going to have 1/3 minus 1 minus 8. Okay. And then this is going to leave me with, I'm going to have a negative 12 plus 9 minus 1/3, which gives me negative 10/3. Okay, that looks good. Now let's move on to part B, the total distance traveled. So if I need the distance traveled, now I have to integrate from 1 to 6 the absolute value of the velocity function. Okay, and so I have to integrate from 1 to 6 the absolute value of t squared minus 2t minus 8 dt. And guess what? It's time to rewrite this as a piecewise function. So absolute value of v of t is equal to, I'm going to factor inside so I can identify the zeros more easily. So that's t minus 4 times t plus 2, right? Okay, so since this is nonlinear, I have to test intervals to see where it's positive and where it's negative. So on the number line, I'm just going to list out where the zeros are. So we'll have negative 2 and positive 4. Okay, so if I pick a number from the interval from negative infinity to negative 2, say negative 3, negative 3 minus 4 is going to be negative. Negative 3 plus 2 is also negative. So negative times a negative, that's positive. Between negative 2 and 4, say you substitute in 0, it's going to be negative. And then from 4 to infinity, it's going to be positive again. Okay, so the particle is moving in the negative direction only between negative 2 and 4. And my interval for the integration is from 1 to 6. So I'm going to have to split it up clearly. So we're going to rewrite our function now. First, I'm going to write the absolute value function out again. So we're going to have t squared minus 2t minus 8 if t is less than or equal to negative 2 or t is greater than or equal to 4, right? Since the quantity inside is already positive, then taking the absolute value does nothing, so I don't need to do anything. However, if t is between 4 and negative 2, then I have to multiply by a negative. Okay, so now let's set up our integral appropriately. So from 1 to 4, the function is defined how? The function is defined as the opposite of t squared minus 2t minus 8. So I'm going to have negative t squared minus 2t minus 8 dt, do not forget the dt, plus, and then you have the integral from 4 to 6, and then I don't need a negative, of t squared minus 2t minus 8 dt. Okay, and then from there the process is pretty similar. So you can just complete the anti-differentiation and you get 98 over 3. Okay, good. Now I'll show you one little way that my calculus teacher taught me long ago how to set these up, and you don't have to do the whole sign chart and testing the intervals. So unless your teacher gets upset at you, this is a quick way to do it. So if you're integrating and you want integral from 1 to 6, absolute value of v of t dt, and you have integral from 1 to 6, you need absolute value t squared minus 2t minus 8 dt, right? And then you identify, okay, the zeros here are at 4 and negative 2. So you know you're going to have to split it up, right, from 1 to 4, and then again from 4 to 6. And the problem, the whole reason why total distance traveled comes out different than displacement is because displacement that's negative, right, when you're moving in the negative direction, cancels out with displacement that's positive. So all you need to do is just say, oh, no, I don't want that to happen. So I'm going to compute this antiderivative, and then I'll take the absolute value of it. I'm going to add it to the other one and take the absolute value of it. Now, one of them is already going to be positive, and it won't need the absolute value. But it doesn't matter. If I take the absolute value of something positive, it's not going to change it, and you're just going to get the same result. So you don't have to test where it's positive, where it's negative. You just break up your interval everywhere that the velocity function is 0, right? So since it was 0 at 4, -2 is not relevant, it's outside the interval. I'm going to break it up at 4, and then you just put absolute value around each of these. Only one of them is going to need it, but you're going to be fine in the end. Okay, it comes out nice and safe. Same thing, 98/3. Only do that though if your teacher will not get upset with you. Okay, so that concludes the lesson on indefinite integrals and the net change theorem.